these are the notes for section 4.9. And in 4.8, we had the contextual situation of having a frozen yogurt stand, so we're going to continue that into today. And we were talking about inverses, and we're going to also continue that into today. And so when we know that when we have inverses, it's swapping the x's and the y's, right? So if we have a function, that maps an x to a y, then that inverse, remember the inverse notation with the little -1 in the superscript, switches that. The y becomes its x, and it maps onto the original x of the function. So what we're going to look at, though, is we're going to look at this more from a graphical standpoint. So if you notice, we're talking about, like I said, the frozen yogurt stand again. Here is that cost. It would cost you to go listen to the jazz band and purchase some yogurt when they were playing there. And so let's just kind of, since we're graphing here, let's just kind of talk about, just go back, quick graphing review, right? This is linear. It looks like y equals mx plus b, but it's actually written as b plus mx as it's written above. So the input of the function is the x, or the z. So the input is z. And remember, the variable z stands for the ounces of yogurt. And the output is the f of z. I think we called that yesterday, we called that D, right? And that is the dollars, or the cost. And so we're going to graph that. So we have 5 plus 0.4z. So it looks like if we, maybe we just count by ones here. So this is 5 and 10 and 15 and 20 and $25. So this is the cost in dollars. And also 5, 10, 15, 20, 25, and this is the ounces. The ounces of yogurt, so Z. So we have an intercept of 5. So we've got an intercept of 5. And then this is the tricky part, right? We go up by 0.4 and over 1, but up by 0.4 doesn't make sense with this graph, with the resolution. Like, I can't count by 0.4s. But I do know that if I multiply by 10, right, then I've gone up, I multiply the 0.4 by 10, I've gone up $4. So at 10, I'm at $9. Remember that from yesterday? 10 ounces of yogurt was would cost us $9. And then 20 ounces of yogurt would then cost us another $4. So that would be 13, which is right there. So that is the linear relationship for the cost it's going to be to go see the jazz band. Okay, so part C here says Sweet Yo's restricts the number of ounces you can get to 24 ounces. What's the minimum amount of money you would need to attend the event, and what's the maximum amount of money? Okay, so they don't want you to buy too much yogurt, right? They're going to restrict it to 24 ounces so that they don't run out, maybe. So let's talk about minimums. So when looking at this graphically, right, the minimum would be the lowest point on that graph. So the minimum would be basically, if you'd go in, you buy no yogurt, right? You just pay to listen to the jazz band. So the minimum would be a z equals 0. And so our f of z is going to be 5 plus 0.4 times 0, which is 5. So that's our minimum. And our maximum then is if we go in and we buy 24 ounces of yogurt. And so, I think I'm spelling yogurt wrong. It's U-R-T, not A-R-T. Anyway, so that would be z equals 24. And so f of z is now 5 plus 0.4 times 24. And that is $14.60. So our maximum is 24 ounces, which is right here. That's 24 ounces. And it's going to be $14.60, which must be that point right there. So this is 24 and 14.60. So that's the maximum. So really anything beyond that, you might say this stuff is not part of the function we're concerned about. So we can just kind of eliminate that. Actually, thinking that through, maybe I'll change colors there. We can kind of eliminate this. Okay, so that is, so this graph has a definite beginning and a definite end, I guess is the point I'm trying to make. And then, you know, as long as I'm putting it on the graph, here is the minimum 0, 5. Okay, so the graph then, since it has a beginning and an end, it has a domain and a range. We can look at it that way. So when we talk about domain and range, the domain then are those x values. So the domain are these x values. So it looks like here that the domain is going to be those x values from 0 to 24, however you want to rate that. We can use a couple different notations. You can just say 0 to 24 ounces. You can just say it verbally too. And then the range is the value, is the corresponding y values. So the range is going to be, well, let's see, we start at 5 and we go up to that 14.6, right? So from 5 to $14.60 is going to be our range. That's dollars. Okay, and so so that's our relationship as we kind of stated it using that function that relates the amount of frozen yogurt to the cost that you're going to incur for the evening. So looking at it now from the inverse's perspective, right? So this was, in part 1, we looked at it from the original function standpoint. Now if you notice, we have the inverses expression here. And so this is also linear. So we know that since this is the inverse, everything is flipped, right? Our input now, notice the questions are kind of the same, right? A is what is the input? Our input is now the dollars. So I'm actually going to literally take this and duplicate it and bring it down here so that word for word it's the same. Our input is now the cost in dollars, And our output, I'm going to do the same thing here. I'm going to duplicate this and bring this down. Our output is now how much yogurt can I buy, right? That's the inverse relationship, which means then that if those flip, then the domain and the range flips, right? Because we're talking about literally flipping our x's and our y's. So now, if we talk about the domain, I don't think I'm going to do a duplicate here. I think I'm going to do just a rewrite here. So now the domain, I'm going to also flip my colors. Now the domain is the cost, the money. So I'll come up here and duplicate this expression. The domain is the cost now. That becomes our input. There we go. And the range now becomes our output. Becomes our ounces of yogurt, that's our output. So I'm going to go up and duplicate that. That becomes our range. And so those have flipped. So we literally have that flipping of what was our domain is now our range. Let me break those arrows a little bit better. And, excuse me, what was our range is now our domain. And so how do we graph that? Well, the easiest way to graph that, because this is also linear. This is also y equals mx plus b. It's hard to see in that form, but we really have f inverse of d is d over 0.4 minus 5 over 0.4. Okay, so your b, you can see your b, trying to decide what color to use here. Your b is this, whatever that number is, and your m is this with a 1 right there, 1 over 0.4. But like I said, that is really hard to see and really hard to graph. There's an easier way to graph the inverse. This is the kind of cool thing. If I want to graph this inverse, I'm just going to swap my x's and my y's. So this is the kind of cool thing. So in other words, I know I have these 2 points. Remember the minimum and the maximum points? We're just going to switch those. So we're going to switch the x's and y's of those points. So instead of 0, 5, we're going to have 5, 0. Let me get my red here. I'm going to, actually before I do anything, let me get my scale here. I'm going to go back to orange. Right, our scale is 5, 10, 15, 20, 25, and 5, 10, 15, 20, 25. This is now our cost in dollars, and this is now our output, which is our ounces of yogurt. Okay, and so like I said, the easiest way to graph this inverse is because we've got a couple of points. We have a beginning and an end, and we know it's linear. We're just going to flip the x's and y's. So instead of 0, 5, this becomes 5, 0. Right? We're flipping the x's and the y's. So 5, 0 is right here. And instead of 24 and $14.60, we're going to swap those. So it's going to be $14.60 and 24. So $14.60 and 24 would be 20. We know 24 is right there, so it'd be right there. So that's $14, and 60 cents, comma 24. And we know that then since we've swapped the x's and the y's, that is our inverse function. Okay, so this is the interesting thing about the inverse function, and that is these lines have a relationship, and it's hard to see when it's on two separate graphs. But because we switched from a y-intercept to an x-intercept, and because we switched these coordinates from x to y and switched it to y and x, these are actually reflections over the line y equals x. So these two graphs, I'm trying to think of what color I want. I think I'll go purple here. Let's go a lighter purple. These two graphs are reflections over, oops, the line y equals x, right? And this line y equals x, notice this is the inverse of itself, right? If we swap the x and the y, we get x equals y, which is the same thing. So here's the inverse. So that line is the inverse of itself. So if we draw that line on each graph, y equals x is just going to be every x value matches every y value. And then I'm going to change that style to a dashed line. Something, maybe a dotted line. That'll work. If we graph that line y equals x, what we see, and we graph it down here, whoops, got a little carried away there. There we go. There's the line y equals x. That's that same line. Let me get the coloring, or the formatting there, y equals x. We can see, and like I said, it's kind of tough to see with it graphed on separate graphs. I'm going to actually superimpose the original line down on this original line. I'm going to graph it down here so you can see that reflection a little bit better. But it's a reflection over that line. So let's do that. Let's take this line and duplicate it and slide it down, there we go, to here, right? It should be right there. Let me zoom in a little bit and get that exact, right? It should be right there. So if you notice, and then let me make that a dashed line, because that was from the graph above. So this is, I'm just going to put a little note here. From above. Okay, so from number one above. There we go. So notice that reflection. Notice that they cross where the y's and the x's are the same, right? So when we swap them, we get the same point. So notice that if we look at this point here, it maps to this point here. Notice that reflection. This point here maps to this point there. So it's a reflection over that line y equals x, which is kind of cool. And it has a lot of visual benefits. Now we can just, by graphically, we can just notice that, that reflective quality, which is kind of cool. So, so looking at question 4, it says if Ross spends $9.40 for the event, how much yogurt did he get? Is there any amount of yogurt he could have purchased that would cost him $9.40 total? So if you remember, $9.40 from the previous class was 11 ounces of yogurt. So this statement is actually getting at the idea of the inverse. This first statement, I'm running out of colors here. We'll go dark green. This first statement is $9.40 was our 11 ounces of yogurt, and this second statement, is there any amount of yogurt he could have bought that would cost him $9.40, is saying 11 ounces, $9.40. So it's really getting at, actually I think I swapped the colors there. Let me make this blue and this green. There we go. If Ross spends nope, I had that right to begin with. If Ross spends $9.40 for the event, how much yogurt could he get? That's the input and the output. So input is $9.40, output is the number of ounces, and then is there any amount of yogurt he could have purchased that would cost him $9.40 total, would be just reversing that and taking that inverse. And so we can see that on the graph as well, that those are inverses of one another. 11 ounces of yogurt coming back up to here. What color was that? Used blue. So 11 ounces of yogurt comes up to $9.40. And then down here, $9.40, that was the dark green. $9.40 would get us 11 ounces of yogurt. So that's that. And so that other point, if I brought that other point down from the other graph, it would be right there. There's that reflection over the line y equals x. So what we're looking at then in terms of learning targets is that we're really looking at that graphical quality. So there's two learning targets. We're going to kind of combine them here. It's actually 3 learning targets total. But the first 2 we're going to kind of combine. And that is that F and the inverse of F are reflections over the line y equals x. And that means the domain and the range flip-flop, right? The x's and the y's flip-flop. So the domain of F becomes the range of F inverse. And vice versa, the range of F becomes the domain of the inverse. Okay, inputs and outputs switch is basically what we're saying here. And then the other thing is kind of an extension of this, and it's really, I haven't really discussed it up here in the notes, but if we look at the original function and its inverse is also a function, right? We talked about passing the vertical line test graphically when we talk about what is a function and what is not a function. And so when that happens, we call that one-to-one. So we talk about this one-to-one phenomenon. So if f is a function, let me rewrite that. F and the inverse are both functions. Okay. So, and that's the idea of one-to-one. If f and its inverse are both functions, then we say that the function is one-to-one. And so what that means is that for every x, there is only one y. I think maybe I should write the word one, not use a number, one y. Every x maps to exactly one y and vice versa. And I'm going to kind of do the check your understanding, because this gets at the one-to-one. This one-to-one phenomenon, and since we haven't really talked about it too much, I want to do the check your understanding just to go through this this idea. So we're going to sketch this. I'll go back to orange, I think. And so we know from our previous unit that this is a parabola, right? And its vertex is 1, 3. And so we know we have a vertex here, it's 1, 3, and it grows like a normal parabola. So let's just graph this: over 1, up 3, and then we go over 1, up 1 on both sides, and over 1, up 1, 2, 3, over 1, up 1, 2, 3, and over 1, up 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, roughly about there. And so we get our parabolic function that looks kind of like this. There we go. Okay, and so if we notice, there's the sketch of f of x, or h of x, excuse me. So the domain here, we can use all real numbers, right? And our range, I'm going to write that out, range is also all real numbers. I'm going to also write domain out. I think that abbreviation probably might be a little confusing because range starts with R as well. So I think I'm going to write domain. There we go. And right, we can use the domain is all reals, right? We use this entire number line as this grows, and our range is not all reals. Wow, that's not true, because our range starts here. Whoops. Our range starts here at 3, and we use everything above 3. So our range is really all values greater than or equal to 3. So h of x has got to be greater than or equal to 3. That's our range. And so it says write an expression of the inverse of h. So the inverse is swapping the x and y's. And we practiced this yesterday, right? The previous class, swapping the x's and the y's. So let's start out by calling this y equals x minus 1 squared plus 3. And then we're going to swap the x's and the y's. So x equals y minus 1. Getting a little sloppy here. Y minus 1 squared plus 3. And then we're going to solve for y. So we're going to subtract 3 from both sides. We get x minus 3 equals y minus 1 quantity squared. And then we're going to square root both sides. So we get the square root of x minus 3 equals y minus 1. And then we're going to add 1 to both sides. So we get y equals the square root of x minus 3 on the inside plus 1 on the outside. And it's kind of important to realize that the x minus 3 is on the inside. I'm trying to make that square root a little bit longer. So it's really important to recognize that the x minus 3 is on the inside and the plus 1 is on the outside. We have to make that really obvious when we write that so that it's not misinterpreted when it's graded. And that also tells us about what's happening to that vertex. So the idea then is if I would graph this, it wouldn't be this entire parabola. It would be over 3 up 1, and it would just be the top part of the parabola. And so if I don't start restricting the domain, then if I want to just graphically draw this inverse, then I could just literally switch the domain and the range, right? So for the inverse, I could say that the domain is all x values greater than or equal to 3, right? That's what this is saying, right? Because this y becomes the x now, we're swapping. And the range becomes all real numbers. And so if that's the case, then if I just draw my inverse, this is 1, 3, so my inverse would be 3, 1, right? That's where that point would map to, is 3, 1. And instead of going over and up 1, I'm going to go up and over 1, right? I'm going to swap those, and down and over 1. And instead of over 1, up 3, I'm going to go up 1 over 3, right? Swapping. Up 1 over 1, 2, 3. Down 1 over 1, 2, 3. And I'm going to start to get the parabola that looks like this. Okay, and that is what I use purple, right? Here's the line y equals x. Right, here's that line of reflection. Oof, my handwriting is getting so sloppy. Let's try that again. Y equals x. There we go. So notice that's the inverse, but we don't typically we found the inverse here, right? We found this inverse here. But if we would graph this, we graphed this in the previous unit, right? If we would graph that, it would only be this. But the strictly speaking, the inverse of this parabola is this pink parabola. And you got to ask yourself, if this is the inverse, right? This is h of x, so this is the inverse h minus 1 of x. Is this inverse a function? So is h minus 1s a function? That's what it's asking. And the answer to that is no. If we look at that, and we try to apply the vertical line test, it doesn't work, right? If we try to apply the vertical line test, here's the vertical line test, it doesn't work. Okay, so H inverse doesn't pass vertical line test. That's one way of justifying it, but there's another way to justify it without even graphing the inverse. Okay, I should be able to look at this and say whether or not it's 1 to 1. Okay, that means, you know, this is another way of saying, is it 1 to 1? Is the inverse of h a function? Let me highlight that. Inverse of h a function. That is another way of saying, is it 1 to 1? That's what that question is asking. And the answer is no, it's not 1 to 1, because when we look at the inverse, this itself, the pink, is not a function. But there's another way to look at that without even having to draw this. We can look at this and say, well, if this is the inverse and we're looking at the vertical line test, and we know the inverse is swapping the x's and the y's, then this vertical line test becomes a horizontal line test on the original function, right? Swapping x's and y's. Vertical becomes horizontal. And so we can simply bypass the whole idea of drawing its inverse by just looking at the original function and saying as our justification, no, because, whoops, let me get the right color there. No, because the original function, h of x, doesn't pass the horizontal line test. I'm actually going to change this color to red, because I'll draw a horizontal line. So coming up here, if we drew a random horizontal line, not getting my color coding right, there we go. We draw a random horizontal line. That's not even horizontal. Let's try that again. There we go. We can see that it touches in 2 points, so this horizontal line test, it doesn't pass. That original function does pass the vertical line test, so the original h of x is a function, but this horizontal line test is saying the inverse is not a function. Okay, that way we don't have to look at the graph of the inverse at all. So let's kind of try that with number 2. Here's a velocity function, okay? And itself, that velocity function itself is a function, right? It passes the vertical line test. But let's talk about its inverse in the context of talking about its inverse without drawing the inverse. So we have this velocity of an ant, the velocity is measured in inches per minute. It's given by the graph of v of t, shown below, for the first 4 seconds. So again, we're going to look at a definite beginning and a definite end, even though it's drawn beyond those 2 locations. So we are literally looking at just this portion of that velocity function. So identify the x-intercepts and interpret these values in the context of the problem. So x-intercepts, right? That is right here. That's at 0, 0. And here at 3, 0. And so the context of the problem says basically attach the units onto this. So at 0 minutes, v of t equals 0. And at 3 minutes, oh, my handwriting is just terrible. Minutes, there we go. V of t is also 0. Okay, so at the beginning, the ant is not moving, and at 3 seconds, the ant is also momentarily at rest, not moving. Okay, so think about the graph of the inverse. How would you label the horizontal and vertical axes? Well, they would switch, right? The horizontal axis would now be our inches per minute, and our vertical axis would now be our minutes, right? Those would swap. And so we have that input / output swap going on there. And C says identify the y-intercepts of the inverse. So think about that. Y-intercepts of the inverse, those are the x-intercepts of v of t, the original function. Right? The inverse is v minus 1 of t. That would be the inverse. I'm going to write that in green. There we go. Okay, so the y-intercepts of the inverse are the x-intercepts of the original function. So the y-intercepts of the inverse become what is written in part A, but swapped. So swapping 0, 0 is still 0, 0. Swapping 3, 0 is 0, 3. All right, and so, but notice it's really saying the same thing, right? At 0, now this is swapped, so this is at 0, we're moving 0 inches per minute at 0 minutes, right? That's what the inverse is, of swapping the x's and the y, and this one's saying we're moving 0 inches per minute at 3 minutes. It says for which values of t is v of t equal to 8. So looking at this, v of t is equal to 8 is right here. So v of t is equal to, when are we going 8 inches per minute? And we're doing that when t equals 1 and when t equals 4. And if you look at this, basically when I drew this line here at 8, this could turn into our horizontal line test. Okay? And so if you notice, even if we move that line, let me take this line and relocate it, right? If we move that line and apply that horizontal line test anywhere, we can see that it crosses the function more than once. So we know that this is not 1-to-1. So we know that v of t is not 1-to-1. V of t is not 1-to-1. Because it doesn't pass the horizontal line test. And so we don't even need to find the inverse to know that this function is not 1-to-1. It is a function though, right? It passes the vertical line test itself. But its inverse wouldn't be a function. It would be something like above, where the inverse would be crisscrossing back and forth onto itself. So it doesn't pass the horizontal line test, so that was not a 1-to-1 function either. So as you go into your homework, that's what you're going to be doing, is you're going to be given a function, and you're going to have to find the inverse based on those reflection, that reflection criteria, and I think that's a puzzle that you solve, so it's kind of self-correcting.